So this question has been asked in JAM 2020. So the statement is, for a system undergoing a first order phase transition at a temperature Tc, which one of the following graph best describe the variation of entropy as a function of temperature T? Okay, so we are given 4 different options, so we have to find the correct one. So let's try to understand the first order transition. So when we say that it's a first order transition, so that means in a first order transition, the Gibbs free energy is continuous. But the derivative of Gibbs free energy G with respect to T, okay, so which we call as the entropy, which is related to the first derivative of Gibbs free energy through this relation, S is equal to dg upon dt at constant pressure, and also the first derivative of G with respect to pressure also, which is volume dg by dp at constant temperature. So both of these derivatives of G with respect to temperature and pressure P, they are discontinuous. At transition temperature Tc. Okay, and the third important point that is related to the first order transition is that they involve latent heat. They involve latent heat, okay, which we call as L. Okay, so the question that's given here, it's related to the third case here. So because we are given that it's a first order phase transition, so that means the transition will take place, transition from one phase into the another phase, that will takes place at constant temperature. Okay, now let's try to figure out which one is the correct answer. So as it's given, I will take an example of a first order phase transition here, which is the example of water vapor system. Okay, this is also an example of first order phase transition. Okay, so that means this transition will take place at certain temperature Tc, a fixed temperature. Okay, now let's try to understand the behavior of water when we are increasing the temperature. Okay, so then what do we expect in general? Okay, so I'm not talking about the transition temperature here. I'm talking about the behavior of the water system below the transition temperature. Okay, when we are far away from the transition temperature. So when we are increasing the temperature of the water, so then what do we expect? The change in entropy with change in temperature. Okay, this should be a positive quantity. Okay, this is what we expect logically. Okay, let's see what happened above the transition temperature, above Tc. So that means when water has changed into vapor system, so in that case the entropy, that is ds by dt, it's also going to be a positive number. But now the question is, what happens at Tc? T is equal to Tc. What is the situation? So that's what we have to figure it out. Okay, so now at T is equal to Tc, for such a case of first order transition, the entropy abruptly changes, or what we can say is it discontinuously it changes to a new value, Okay, so there is an abrupt transition in the entropy when the phase transition it's occurring at T is equal to Tc. Okay, So, and let's try to understand what happens to the heat capacity. Heat capacity Cx, where x simply represents the constraint. It could be constant of constant temperature, constant temperature, but pressure, or constant of volume also. Okay, so Cx, this is defined by dq by dt. Okay, so what is dq? That's the energy exchanged. Okay, so at critical temperature, we will multiply it by Tc and then change in entropy. So let's say if we are talking about the water vapor system, so the entropy corresponding to the final state minus entropy corresponding to the initial state. Final state is here. It's a vapor system. Vapor minus S water and divided by what is the change in temperature, dt here, because this process, it is taking place at constant temperature, so dt will be 0. So that means, so this will give a spike in heat capacity. Okay, so the conclusion is, so whenever we are talking about a first order phase transition, so the entropy, it changes abruptly, but it's not having any kind of spike in its behavior when at the phase transformation point. Okay, so that means at the critical temperature. Okay, so therefore the correct option is D here. So here entropy change below the critical point Tc, if you just take a look at the slope of this ds versus dt, it's positive in this region. Okay, because we are increasing the temperature, that will result in increasing entropy of the water also. Okay, so here also we are having a positive change in entropy with the change in temperature, but at the critical temperature, the entropy value here, when this critical temperature has been reached, the entropy value suddenly increases to adjust its new value corresponding to the second phase. So this is the correct option. So this is the next question that appeared in JAM 2020. The question is, in which one of the following limits the Fermi direct distribution NFET, that is equal to 1 upon exponential E minus mu by kt plus 1, and Bose-Einstein distribution NV, that is equal to 1 upon exponential E minus mu by kt minus 1, reduces to Maxwell-Boltzmann distribution. Okay, here E, that is the energy of the state, and mu is the chemical potential, and kV is the Boltzmann constant, and T is the temperature. So in order to find the correct option, let's first write the general expression for the distribution function. Okay, the general expression for distribution function for all three statistics can be written like this. Let's denote it by n. Okay, n is equal to 1 divided by exponential E minus mu by kt. Okay, plus a. Now what is a here? Where a, when a this is equal to 0, then this particular case corresponds to Maxwell-Boltzmann distribution. Okay, distribution. And when a this is equal to plus 1, this particular case corresponds to Fermi direct distribution. Okay, and when a this is equal to minus 1, this case corresponds to Bose-Einstein distribution. Okay, now we have to figure out that under what condition. So that means what is the condition between that exists between the E minus mu and kVt. Okay, so to figure out the essential conditions, what we will do is we will assume that let the exponent, so that is E minus mu by kVt, let this is equal to x. Okay, And if we further assume that if this quantity E minus mu upon kVt, this is much greater than unity. Okay, so that means what we can say is, if E minus mu, this is much larger than kVt. Okay, so that is, if this is because we considered it to be equal to x, so that means what I can do is I can rewrite this as this is equal to x. Okay, so that means if x is much larger than unity, so this implies e power x, this is also greater than unity. And if that is the case, so then in the distribution function, for instance, if I take an example of the Fermi Dirac distribution function NFD, okay, where FD speaks, it stands for Fermi Dirac. Okay, so this becomes equal to exponential E minus mu upon kBt, and then here a is equal to plus 1 here for Fermi Dirac distribution. If that is the case, so in that case, because e power x, so that means this quantity, it's going to be much larger than unity. So then we can neglect this quantity. So then we can approximate this to be equal to 1 upon exponential E minus mu upon kVt. Okay, and which is further equal to exponential negative of E minus mu upon kVt. Okay, similarly we can approximate the Bose-Einstein distribution also under this approximation. The same approximation if you apply for the distribution function for the Bose-Einstein case, so then that becomes here exponential E minus mu upon kVt minus 1. So again the same scenario. So this quantity, it's going to be much larger than unity, so we are going to neglect this this factor here. Okay, so that means this is further equal to 1 upon exponential E minus mu upon kVt, which is equal to exponential minus E minus mu upon kVt. And if you recall the case when a is equal to 0, so that means when this quantity here, this is equal to 0, we obtain the expression for the Maxwell-Boltzmann distribution, which is nothing but 1 upon exponential E minus mu by kt. Okay, or I can rewrite this as exponential minus E minus mu upon kVt. Okay, so therefore under this condition, what is the condition? Essential condition, so that all these three distributions, they are identical. So the essential condition is that when E minus mu, this is much greater than kVt. Okay, so therefore our correct option is which one? It is C. Okay, so C is our correct option. So C is correct. So here the statement is, we are given a system of n classical particles at certain temperature T. Okay, so each of which can have two possible energy states. So we are given a system of n classical particles, and there are two energy states in the system. Okay, so let's label these energy states at 0 and E. Okay, and it's given that the number of particles in the lower energy levels, it's also given the number of particles in the lower energy level, there, that's n0, and the number of particles in the upper energy level, they are ne. And what the essential condition is that the total number of particles in the system, that is equal to number of particles in the upper energy level plus number of particles in the lower energy level. Okay, now the question is, the ratio between n0 and ne is related by So we have to look for the correct option. Okay, so if we recall the Maxwell-Boltzmann distribution, okay, the ratio between the number of particles which are there in the particular energy states, so that's given by, for instance, here n2 upon n1. Okay, where n2 represents the number of particles in energy state 2 and n1 represents the number of particles in energy states 1. So that is equal to the exponential minus the energy corresponding to the the energy corresponding to the upper state, okay, minus the lower energy. Okay, so here if we compare this situation with the present case, so this is equal to n e upon n0. This is equal to how much? Exponential minus e minus 0. And here I forgot to write the Boltzmann factor here, sorry, that beta factor here, kVt. Okay, so here also you will have kVt. So we can rewrite this relationship further, as because here in the options we are given n0 by ne, so we can rewrite this equation as n0 by ne, that is equal to, so we have to simply invert it. Okay, exponential beta e, where beta is nothing but it's 1 upon kVt. Okay, so beta is 1 upon kVt. So therefore the correct option is which one? It's n0 by ne, that is equal to exponential beta e. So therefore B is the correct option. The statement is the root mean square velocity, the root mean square speed of hydrogen atom at 500 Kelvin is Bh, and helium atoms at 2000 Kelvin Bhe are related as. So we have to find the relationship between the RMS speed of hydrogen and helium at given temperature. So the general expression for the root mean square speed is V RMS. This is equal to 3 kT upon m. Okay, or what you can write is this is proportional to the temperature and divided by the molecular mass of the gas molecule. Okay, so now for hydrogen, the temperature is 500 Kelvin. Okay, and let's say its mass, it is mh, because it's having two nucleons, so I will write 2m, where m stands for the mass of one nucleon. Okay. Similarly, for the case of helium, The denotes the temperature at which helium is kept. It is 2000 Kelvin, and mass of helium, if I denote it mhe, because helium it will have 4 nucleon, okay, then 4 times m. Now we have to find the relationship between the root mean square speed of hydrogen and helium. So let's divide these two quantities. Vh, that's the root mean square speed of hydrogen divided by RMS speed of helium. Okay, then we will make use of this expression. So this will be equal to, okay, it's th divided by mh and then multiply by m helium upon t helium. Okay, and if you substitute these values, okay, we will obtain it's 500 and then divided by twice m. Ultimately m, this m will cancel with this m. Okay, so I'm writing only 2 here. Okay, just for the clarification, 2m and then 4m divided by 2000. Okay, so after solving it, you will obtain this is equal to 0.71. Okay, so that means VH, this is equal to 0.71 times V helium, or in other words you can write this as 10 times the RMS speed of hydrogen, that is equal to 71 times, sorry, 7 times. Okay, so if I'm taking only up to first decimal place, so times VHE. Okay, so this clearly indicates that the RMS speed of hydrogen, this is less than RMS speed of helium for the given conditions. So therefore B, that is the correct option. Let's take a look at the next problem. The statement is 1 mole of an ideal gas having specific heat ratio, that is gamma, of 1.6 is mixed with 1 mole of another ideal gas having specific heat ratio of 1.4. Okay, if Cv and Cp are the molar specific heat capacities of the gas mixture at constant volume and pressure respectively, which of the following is R correct? Okay, here R denotes the gas constant. Okay, so in principle we can do this problem in two different ways. Okay, so I will discuss both of the methods. Okay, and then at the end we will see that one of them is more precise compared to the second one, and the answer matches with, almost correctly with the both approaches. Okay, so let's try to understand. Here we are given that the number of moles of first gas. Okay, remember that the gases, they are ideal. Okay, so it's 1. Okay, and the value of adiabatic index gamma 1, that is equal to 1.6. so this information is given to us. Okay, so if we recall the discussion that we had during the calculating a degrees of freedom, so from there we can also evaluate the value of adiabatic index for any kind of gas. Okay, so here this value of 1.6, this is roughly equal to a gamma value of 5/3. Okay, which corresponds to a monatomic gas. Okay, so what we can do is from here we can conclude that the heat capacity at constant volume for this particular case, it's going to be 3/2 R per mole. Okay, now let's take a look at the second information, which is related to the second gas N2. The number of mole of the second gas, it's also 1, and the value of gamma, I will call it as gamma 2, this is equal to 1.4. Okay, and this is, so that means gamma 2 here, this is equal to 7/5. Okay, so this conclude that Cv2, it's for the diatomic gas. Okay, so diatomic gas, it's having 5 degrees of freedom, 3 translational degrees of freedom and 2 rotational degrees of freedom. So Cv2 will per mole will come out to be equal to 5/2 R. Okay, so now, so when these two gases, they are mixed, okay, when they are mixed, so then the common heat capacity for the mixture, if I denote that as Cv mixture, Cv mix, that is equal to N1 Cv1 plus N2 Cv2 divided by N1 plus N2. Okay, so here simply substitute the value of N1 and N2, that is 1 here. Okay, and Cv1 and Cv2, the value that we have written here. And if you do that, after substituting the value of these quantities, you will obtain this result to be equal to 2R. Okay, so once Cv mix is obtained, then from here we can obtain the value of Cp. Okay, Cp for mixture. Okay, and this is equal to Cv mix plus R. So that means 2R plus R, that will give you 3R basically. Okay, and from here we can find the value of gamma mixture. So gamma mixture will be simply the ratio of Cp mix divided by Cv mix, and that will give you how much? 3R by 2R. Okay, so 3R by 2R, and that is equal to 1.5. Okay, now let's take a look at the second method, which is a little more precise as compared to this one. Okay, so here this information it will remain as it is. So okay, this information, but here for the calculating of the value of gamma, so we will use the other method. Okay, so as we know, for an ideal gas, Cp minus Cv, this is equal to R. Okay, and if we divide both sides by Cb, so from here we obtain Cp upon Cb minus, when we divide Cb by Cb, we will obtain 1 here, and this is equal to R upon Cb. Here Cp by Cb is what? This is equal to gamma. So that means R divided by Cv, this is equal to gamma minus 1. So from here we can arrive at this result: Cv is equal to R upon gamma minus 1. So with the help of this result, we can calculate the value of Cv mix here. Okay, so here Cv mix, we will make use of the same expression here also. Okay, so let me go to the next page. Okay, so Cv mix, this is N1 Cv1 plus N2 Cv2 upon N1 plus N2. Okay, so here because Cv is equal to R upon gamma minus 1, so when we will replace Cv1 will be R upon gamma 1 minus 1, and Cv2 will be R upon gamma 2 minus 2. Okay, so when we will do that, so at the end R will come outside, so I can write this as R divided by 2, where 2 comes from here, N1 plus N2, that will give you 1 plus 1, that is equal to 2. So R divided by 2, and then the terms that remain inside, this is N1 is 1, so nothing will happen, so it's 1 upon gamma 1 minus 1 Cv1, that's gamma 1 minus 1, R upon gamma 1 minus 1. R we have already taken outside, so gamma 1 is how much? This is 1.6, it's given 1.6 minus 1 plus 1 upon gamma 2 minus 1. What is gamma 2? That is 1.4 minus 1. Okay, and after evaluating, this comes out to be equal to 2.08 R. Okay, now Cv mix we have evaluated. Now from here Cp mix will be Cb mix plus R. So that means this quantity 2.08 R plus R. So this is equal to 3.08 R. So therefore gamma value for the mixture, this is Cp mix divided by Cv mix, and this is equal to 3.08 R divided by 2.08 R, and this comes out to be equal to 1.48. Now take a look at the options that are given to us. Okay, so we are having Cb mix value, it's 2.08 R. Okay, so here the one of our result matches with option A. Okay, and then we are having a gamma value of Cp by Cv, that is equal to 1.48. The another result matches with this result. Okay, so now we can also compare the two approaches that we used for solving this problem. In the first approach we obtained Cv mix, that is equal to 1.5. Okay, so sorry, the gamma mixture, it's 1.5. Okay, so this is almost, if you just approximate up to first decimal place, this is again the value that's almost close to 1.5. Okay, and what is Cb? Cb for the mixture, it's 2R basically. Okay, 2R. So here we have obtained by the exact approach, it's 2.08 R. Okay, so therefore option A and C are correct. Okay, the statement is an ideal gas undergoes an isothermal expansion along a path AB. So path AB, it's given to be isothermal process. Adiabatic expansion along BC. Okay, BC is an adiabatic process. Okay, because BC, it's more steeper than AB. Okay, and then isobaric compression along the line CD, and then again there is another isothermal step here. This is an isothermal step, isothermal compression D to E. Okay, and then and adiabatic compression along EA, E to A, that is an adiabatic compression again. Okay, as shown in this figure. The work done by the gas along the process BC is 10J. So what kind of process BC is? This is an adiabatic process. Okay, so the work done is given along the process BC. Okay, that's the first information that's given to us. The change in internal energy along process EA. Okay, the another information that is given to us, that is the information related to this process. Okay, and how much is the internal energy change? That is 16 joule. The absolute value of the change in internal energy along the process CD. So now we have to evaluate what is the change in internal energy along CD. Okay, this is a very simple question. The only point that you have to remember is, for any cyclic process, okay, so any kind of cyclic process, when you start from the some initial equilibrium point, let's say this is at this point A. Okay, and then if we are performing various steps in between, and again we are arriving at the same starting point. So that means when initial and final equilibrium states they are identical, so the net internal energy change during that complete cycle, delta U cycle, this is going to be equal to 0. Okay, because the internal energy, it simply depends upon the initial and final equilibrium state. Okay, it has nothing to do with the intermediate stages. Okay, so now we will make use of this point here. So net internal energy change along the complete cycle, we can write delta U cycle, this is equal to delta U when we are performing process AB, okay, plus delta U when we are performing the process BC, okay, plus delta U when we are performing the process CD, okay, plus the internal energy change when we are performing process D to E, plus delta U D to E, and then plus the internal energy change when we are performing the process E to A, delta U E to A. Okay, and this should be equal to how much? This should be equal to 0. Now let's call this as equation 1. Okay, now what kind of process AB is? AB, it is an isothermal process, and as well as D to E, this is also an isothermal process. So in isothermal processes, so in isothermal process, delta T is equal to 0. This implies delta U, this is also 0. Why? Because we are given that it's an ideal gas, and for an ideal gas, the total energy is it's purely kinetic in nature. Okay, and if temperature it's not changing, then its internal energy will not change. So this means, because AB and DE, they are isothermal processes, so that means delta U AB is equal to delta U DE, and this is equal to 0. So here this is 0, and then DE, this is also 0. Okay, now let's try to understand what happens when we are performing process BC. So it's given that the work done by the gas along the process BC, it's 10 joule. So when we are moving along path BC, the work done is given to us, it's 10 joule. Okay, so we will write the statement of the first law of thermodynamics here. So du, this is equal to dq minus dw. But now remember that process B to C, it is an adiabatic process, so dq will be 0. Okay, and what is dw? It's given that the work done by the gas when we are moving along path BC, it is 10 joule. Okay, so that means du is equal to minus 10 joule. Okay, so this means the internal energy change when we are moving along path BC, so du BC, this is minus 10 joule. So this quantity, it is minus 10 joule. Okay, now let's take a look at E to A. So E to A, it's already given that the internal energy change is how much? It is 16 joule. So that means this number is also given in the statement of the question. This is 16 joule. Okay, now we can calculate this quantity because that's the only one that's left in the equation. So delta U cycle equal to 0. This ensures that this is equal to 0 means 0 minus 10J plus delta U CD plus 16, that is equal to 0. So this means delta U along path CD, this is equal to 16 minus 10, that will give you 16 minus 10, that will give you 6 joule. Okay, and when we will take it on the other side, so ultimately this is minus 6 joule. But we are asked the absolute value of change in internal energy along the process CD is. So therefore, because we are asked the absolute value of the delta U CD, so that means delta U CD, the absolute value is equal to 6 joule. So 6 joule is our answer. Let's take a look at the next question. The statement is, a body at a temperature T is brought into contact with the reservoir at temperature T2. Okay, the thermal equilibrium is established at constant pressure. The heat capacity of the body at constant pressure is Cp. Okay, the total change in entropy of the body and the reservoir in units of Cp is. Okay, so we have to give the answer up to 2 decimal places. Okay, so what we are given is, we are given a body, okay, which is at temperature T, and its heat capacity is also given to us, it is Cp. Okay, now it is brought in contact with a big reservoir which is at temperature 2T. Okay, so when they are brought in contact with each other, so ultimately they will form a composite system. Okay, and finally what will happen after joining these two? Okay, so they will form a composite system, and ultimately the final temperature of both the body, the given body, and the reservoir, they will equilibrate at the temperature of the reservoir. Okay, so that means for the given body, so let me call this as body, the temperature is changing from T to 2T. Okay, and it's taking a certain amount of heat from the reservoir, whereas what is happening with the reservoir, its temperature is not changing, but it's giving heat to the body. Okay, and its temperature it's fixed. Okay, now we have to evaluate the total change in the entropy of the body and the reservoir. Okay, so let's try to find out what is the entropy change for the body first. Okay, and if I call the entropy change for the body as delta S B, where V stands for the body, this is given by dq by T, and because the temperature it's changing from T to 2T. Okay, and it's also given that process is taking place at constant pressure. Okay, so this is further equal to Cp dt upon T and T to 2T. Okay, and this comes out to be equal to Cp outside because it's constant. Okay, logarithmic of temperature, and the limit of integration goes from T to 2T. So this will give you ln logarithmic of 2T divided by T, or this is equal to Cp ln 2, and this is equal to 0.693 times Cp. Let me call this as equation 1. Okay, now we have to evaluate the entropy change for the reservoir. Okay, but for calculating the entropy change for the reservoir, first we need to know what is the energy exchanged by the reservoir when it came into contact with the body. So in this particular case, the heat is given by the reservoir, but that process is taking place at constant temperature. It's giving heat to the body, okay, but its temperature is not changing, and this process, it is taking place at constant temperature. Okay, so that means the delta S for the reservoir, this will be with the negative sign here, and dq upon constant temperature of the reservoir, which is 2T. Okay, so the reservoir is giving heat to the body at a temperature of 2T. Its temperature is not changing. And here what is dq? Dq is the amount of heat which is given by the reservoir. Okay, and exactly the same amount of heat will be taken by the body. So we will calculate this energy exchange, the energy exchange between these two from the information that is given for the body. Okay, so dq will be, this is further equal to minus 1 by 2 as it is, and then dq is how much? That is Cp times delta T, where delta T, that's the change in temperature of the body here. Okay, so this is equal to minus 1 by 2T, but is delta T for the body, that is 2T minus T. Okay, 2T minus T. Okay, so and then multiply by Cp. So ultimately this is equal to minus Cp divided by 2. Okay, so therefore the net entropy change will be how much? Delta S total, that is equal to delta S body plus delta S reservoir. Okay, and if you add these two numbers, okay, we will get at the end is we have to substitute this value here, and then minus Cp by 2 here, and if you do that, at the end we will obtain Cp will come outside, and inside we will have 0.6 93 minus 0.5, and this is equal to 0.193 Cp, or we can approximate it up to 2 decimal places, 0.19 Cp. So therefore here the answer is 0.19. Okay, and here I just want to emphasize on the point, because the dq here we evaluated from the information that is given to the given for the body, not for the reservoir, because if you apply the principle of calorimetry here, whatever amount of heat is taken by the body, the same amount of heat is given by the reservoir. Okay, so that's why this information is obtained from the information given for the body, not for the reservoir. Let's continue with the next question. It's a numerical answer type question for 2 marks. Okay, the statement is 1 mole of an ideal monoatomic gas at pressure P, volume B and temperature T is expanded isothermally to volume 4B. Okay, so this is an example of isothermal expansion. Thereafter the gas is heated isochorically, so that is at a constant volume, till its pressure becomes P. Okay, if R is the universal gas constant, the total heat transfer in the process in units of RT is, okay, so we have to find the final answer up to 2 decimal places. Okay, so let's continue with the first step of the process, which is isothermal expansion. Okay, so first step is isothermal expansion. Okay, and it is an ideal monoatomic gas. Okay, this is an ideal monoatomic. So ideal monoatomic gas, so that means it's given that number of moles is 1, and it's because monoatomic gas, so that means the corresponding heat capacity at constant volume for 1 mole of gas will be 3 by 2 R. Okay, which is further equal to 1.5 R. Okay, now because it's isothermal expansion, okay, so that means for this case dt, this is equal to du, and that is equal to 0. Okay, now by applying the first law of thermodynamics, we can evaluate the corresponding heat changes involved during this process. And if I call this is du1. Okay, so applying first law of thermodynamics, du1, that is equal to dq1 minus dW1. Okay, so du1 it's 0 as I just argued earlier. Okay, so that means dQ1 in this process will be how much? dQ1, which is nothing but d the work done that that is obtained during the isothermal expansion, because it's 1 mole, so the corresponding work done will be RT ln the final volume, which is 4 times the initial volume. It's given in the statement of the question. It's 4B. The gas expanded from B to 4B. So logarithmic of 4B upon initial volume B. Okay, so that is equal to RT ln 4. Let this is equation 1. Okay, now come to the second part of the question. What is that? It is iso, then the gas is heated isochorically. Okay, gas heating isochorically, isochorically. Okay, so that is dV, this is equal to 0. Okay, so that means when dV is equal to 0, so that means no work is done, dW is 0. Okay, so if I write the corresponding internal energy change in this case as dU2. Okay, dU2 that is equal to dQ2 minus dW2, because here it's the dW2, it's 0 as I said earlier. Okay, so that means dQ2 it's nothing but the change in the internal energy when this particular process is performed. Okay, so how much is going to be dU2? So dU2, so I will write dQ2 it's equal to dU2, and this is equal to how much? It's the number of moles, and number of moles they are given to be 1. Okay, so NCB delta T, where CV is the heat capacity at constant volume for the corresponding gas. Okay, because it's monatomic gas, so I will write here it is 3/2 as I have written in the beginning here, 3/2. And then what is delta T? Okay, so I'm going to write here the delta T value here, where 40 was the initial temperature. I'm going to explain it in a moment why the 40 was the temperature in the initial state here before we started this process. Just let me write it first here, 40 minus T, the final temperature here, and then it is finally equal to 9/2 RT, or this is equal to 4.5 RT. Okay, now let's try to understand why the factor of 40 came here. Okay, so let's take a look at the first step when the process it occurred isothermally. Okay, and the volume changed to from initial volume V to 4B. Okay, in the first step I'm talking about. Okay, the isothermal step I'm talking about. Okay, the isothermally volume changed from B to 4B, and because it's an ideal gas, so this is supposed to satisfy this equation PV equal to RT. Because it's isothermal process, temperature is going to be constant, R is already a constant. So when volume changed from B to 4B, to make this quantity as constant, or to make this quantity to be equal to RT, when volume changed from B to 4B, the pressure will change from P to P/4. Okay, so here when we started this process, the initial pressure was P/4 here. So for this case, the initial condition was P/4. Okay, and then again with this pressure P/4 in the beginning, because it's an ideal gas, it's again going to satisfy the ideal gas equation further, but now the process is taking place isochorically. Okay, so that means when PV is equal to RT. Okay, so now for this case, this is going to be constant, fixed, but the initial pressure is P/4. So initial condition is here Pi, this is equal to P/4. Okay, and what is written in the statement of the question? The gas is heated isochorically till its pressure becomes P. So that means the final pressure is how much? Final pressure is P. Okay, so now you have fix B, fix R, so that means whatever changes you are doing in the pressure, the same changes will be reflected in the temperature. So here the pressure has changed from P/4 to P, so that means pressure has increased 4 times. okay, from initial value to final value. So that means the temperature has changed from initial value of T to final value of 4T. So for that reason I have taken here 4T as the final temperature and T as the initial temperature. Okay, so now we have evaluated dQ1 and dQ2. So now we are supposed to find out what is the net heat energy, the net heat transfer during the process. Okay, let me introduce another page here. Okay, so the net heat changes that take place during the entire process, let me call this as dQ, which is equal to dQ1, which is the heat change involved in the isothermal expansion of the gas, plus heat changes that involved during the isochorical step of the process. So dQ1 is how much? This is RT ln4 plus dQ2 is how much? This is 4.5 RT. Okay, and I can rewrite this as RT 2 ln2 plus 4.5. okay, so ln2 is it's 0.693, and when you substitute the value these the numeral values, this comes out to be equal to 5.886 RT. So that means up to 2 decimal places I can write this as 5.89 RT. okay, that's our final answer. So that means in terms of RT, here we can write our answer will be 5.89. Let's take a look at the second question. It also appeared in JAM 2020. Okay, the statement is: consider two spherical perfect black bodies with radii R1 and R2 at temperatures T1 equal to 1000 Kelvin and T2 is equal to 2000 Kelvin respectively. They both emit radiations of power 1 kilowatt. The ratio of their radii R1 by R2 is given by. Okay, now if we recall the result, the power radiated by a black body, that is, if we call this as P radiated, this is equal to A sigma T power 4. Okay, where A, this is the area of the body, here black body, area of black body, and sigma, this is Stephen constant, and T is the temperature of the body, Okay, so we are given some information. So what is that? The temperature T1 of the body 1, this is equal to 1000 Kelvin. Temperature T2 of the second body, this is equal to 2000 Kelvin. And it's also given that power radiated by both of these two bodies, that is P1, this is equal to P2, and this is equal to 1 kilowatt. Okay, now we have to find what is the ratio of their radii, that is R1 is to R2, this is equal to how much. Okay, so now what I can do is I can write here the power radiated P1, this is equal to, that's the area, or you can say surface area, which is equal to, if I write the Stephen constant, it's common in both cases, so I'm writing it first, and then the surface area, which is equal to 4 pi R1 square, and then temperature of the respective body and its power 4. Okay, similarly I can write expression for the power radiated by the second body, the constant multiply by surface area 4 pi R2 square, and then T2 power 4. Now if we take a ratio of these two quantities, that is P1 by P2, okay, it's given P1 is equal to P2, this is equal to 1 kilowatt. So that means this ratio will be equal to unity, and if we divide these two expression, so this will give a 4 pi sigma, that will cancel, okay, and then we are left with R1 by R2 its whole square multiply by T1 by T2 its power 4. So after rearranging this expression, ultimately we obtained R1 by R2, this is equal to T2 by T1 and its square, okay. What is T2? It's 2000. It's given 2000 divided by 1000 and power 2, okay. So we are left with only 4. So therefore ratio of the radii, this is equal to 4. So answer will be 4.